you essentially have something that's totally unpredictable. Winds that are typically only seen on planets not named Earth, like Venus.
So how is a tornado formed?
That's a really good question. And we don't actually know all of the gory details, but in principle, what happens is we have rotation that gets developed at the ground, and then we have a thunderstorm that's kind of overhead of that ground-based rotation. And what happens is the rotation that's below is sucked into the middle and pulled upward, very similar to an ice skater. As she pulls her arms in, she spins faster. The same principle applies to a tornado. Now, some questions surrounding that is like, where does that ground-based rotation come from in the first place? Why is it only there sometimes? And those are things that we're answering right now, we're hoping to answer.
Why has it been difficult to figure that out?
It's really difficult to actually get measurements of ground-based rotation because we don't have instruments that are capable of observing them in a continuous manner. And the second problem is that we just don't know when and where this rotation is going to develop in the first place because it's not always present. So trying to set up instruments that are in the right place at the right time and in a way that we have enough instruments to spatially cover an area has essentially proven to be logistically impossible to this point.
When you kind of look at the start of a tornado, is it something that would start at a point like, say, the tip of my finger and then get bigger? Or is it like, how big is the beginning of the tornado?
Oh, that is a really good question. It would typically be broader, actually, broader than the visible intense column of rotation that defines the tornado. So it's typically broad, and then the spin increases as the scale contracts to something very narrow.
So when it, like the ground-based rotation, if I understand this correct, so like the tornado doesn't start rotating at the top and then go down to the ground, it starts at the ground and then goes up?
Yeah, that's correct. So it's actually a misnomer. Like our eyes cue into the funnel cloud, and obviously the funnel cloud develops in the sky and then works its way down. But in order to actually have a full-fledged tornado, you need to have that ground-based rotation present in the first place. So oftentimes what we end up seeing happen is we see that rotation start to organize at the ground, and then it intensifies in the storm above, and that intensification in the storm above at the same time as that intensification of the ground-based rotation essentially works together to kind of complete almost like a rotational circuit, if you would.
Why does it seem to be only in certain places, only at certain times?
If you look at a world map of, I don't know if this can be found on the internet easily, but somewhere you can probably find a map that shows the distribution of tornadoes worldwide. And what lights up flashing red is the so-called Tornado Alley of the United States, roughly from Texas northward up to the Dakotas and eastward to roughly the Mississippi River. There's also an extension that extends east of the Mississippi into the southeastern United States.
And that has to do with the physical geographic configuration of that part of the country. We have a warm, moist source for air coming up from the Gulf of Mexico. We have elevated terrain towards the west. That includes both the Colorado Rockies. So we get low pressure systems developing on the eastern side of those Colorado Rockies, which promote southerly winds, which suck up that warm, moist air from the Gulf of Mexico. And then further to the southwest, we have a geographic feature called the Mexican Plateau, which advects or moves air from the southwest towards the northeast, which trajectory-wise takes it up over the Central Plains area, and that contributes to the formation of a feature known as the dry line. And the dry line is a known source for forming storms in the first place. And then that air also actually contributes to a stable layer immediately above the ground, which allows for the surface conditions to become really juicy and moist and wet and warm, and eventually, once it gets warm enough, we can have explosive thunderstorm development. So without that stable layer above, we would see more modest kind of trickling of intermediate type thunderstorms. When we look at specific locations, like a specific town or a specific area near a mountain, for example, We do know that in some cases, depending on the overall larger scale environment, we can locally contribute to environments that are more favorable for tornado formation because of specific geographic features that exist at an exact location. So for example, there are certain river valleys that are known to change the winds in a manner that actually creates tornadoes more efficiently than if those river valleys weren't there, for example. Similarly, there's some terrain features, for example, in Alabama, where we tend to see enhanced tornado formation on one side or the other side of a topographic feature. And again, we relate that to local modification, primarily of wind direction and wind speed, that for basically a short time frame as a storm is passing over it, locally enhances the environmental conditions and essentially tips the scale toward a scenario that's more favorable for tornadoes than if that terrain feature weren't there in the first place.
When you talk about like terrain features, right? Like the first thing, are we talking about like, okay, we built this row of houses in a way that funnels the wind? Are we talking about like golf courses, or like we've tunneled into the side of a mountain or something? Like what do you mean by like topographical features?
So I basically mean kind of the natural features in the land. So hills and valleys, and to a degree some smaller mountains. And now if you have a really large mountain, typically that's not going to be favorable for a tornado to survive. It's not going to be able to go up and over. But certain smaller scale hills and escarpments or valleys are known to locally modify the direction and speed of winds in that sense.
So it's not like Steve built a house at the end of a cul-de-sac and now we've got tornadoes here because he didn't build it the way everybody else did or something.
That's right. Although with that in mind, I am participating in some work with a civil engineer where we're looking at how individual houses and buildings modify tornadoes as tornadoes are approaching them. And then similarly, like if you were to destroy those buildings by the tornado, how does that then impact the tornado as it moves on further in its life? So there are actual physical effects that are associated with individual buildings too, but it's not going to probably make the difference of whether or not a tornado forms in the first place. But when you get a bunch of buildings together in certain block-like construction configurations, it may end up actually affecting the tornado either for good or for bad.
We could have like tornado-proof buildings, or like, hey, build this thing here and it's going to stop the tornado or deflect it or something like that.
Possibly in the future, you know.
Just to kind of reiterate, it's not the weather, it's the weather and that specific geographical feature of the land.
That's generally correct, yeah.
So like when you think about a tornado, like, okay, it's spinning, but like what's happening inside of the tornado?
Inside the tornado, there's typically sinking air, actually, down to a point. It's technically you could find a singular point in there where the wind is calm. I mean, we talk about the eye of the hurricane, how it's this relative calm surrounded by hell on earth, a violent wind surrounding the eye, which that's the eye wall of the hurricane. Technically, a tornado has an eye as well. It's just that it's so tiny that there's a very small chance you'd actually ever find it. And even if you did happen to pass through it, you're talking about a second or less when it would be relative calm in there. You wouldn't remember it as being a calm event. So along the outskirts of the tornado, violent winds, you've got, it's not even so much the wind that is as dangerous as the stuff that's embedded in the wind. 2x4s, large pieces of debris, automobiles can be embedded in the tornado flow. You're talking about massive impact, obviously. So one other thing I would say that's often lost is it's not just the rotational part of the wind in a tornado that's violent. There's a violent updraft as well. So you can have 100-mile-per-hour winds going around the tornado, but the up component can also be 100 miles an hour at, say, not that far off of rooftop height. But when you hear stories about really heavy debris like cars or automobiles, railroad cars, though, being jettisoned, that stuff, I think, can really only happen if the heavy stuff's also embedded in air that has a very strong upward component.
And the upward component, that's part of what I would consider to be the tornado, or is that in front of the tornado, or like where is the upward
That's
part?
that's right on the edge of the tornado. Sometimes in tornado video, you can see that stuff on the edges going up pretty violently. It would be right on the edge of the visible funnel typically.
Can we predict them?
We cannot predict tornadoes with very good accuracy. We can predict and I guess I should say, we can predict and acknowledge environments that are favorable for tornado formation.
Even 2-3 days in advance, we sometimes can say, hey, central Kansas, 3 days from now, if there's going to be action, that's where it's going to be. But when we get down to, say, T-minus 30 minutes and storms start popping up on radar, we have essentially no ability to say, okay, storm number 1 is going to make a tornado 17 minutes from now, and that tornado will last 5 minutes. Storm number 2 won't make a tornado, but storm number 3 is going to make an even more intense tornado, but starting in 32 minutes. We're never going to be able to have that level of specificity. And it's precisely because when you try to start determining things on a point-by-point basis, you really lose predictability horizon. And that's ultimately because of what's known broadly as the fancy term is nonlinearity of the math, nonlinearity of the physics, but the physics are governed by mathematics ultimately, or at least math is kind of the language we use to try to explain the physics. I think for me, a great analogy is the Plinko game on Price is Right. Ever watch Plinko?
Yeah, I know.
Okay.
You drop the thing, it bounces back and forth.
You drop the thing and it bounces around. If you move where you drop the Plinko chip by a millimeter up at the top, how do you think the outcome is going to be affected? It's not going to be affected by a millimeter at the bottom, or it might be, but that would be just luck. You could move it a millimeter at the top and it could end up a foot. You essentially have something that's totally unpredictable. It's the same thing happening naturally when it comes to the atmosphere. We're really good at describing the big picture, but then as you go to smaller and smaller scales, it's like you're hitting different little pegs along the way. And if you're trying to predict exactly where that disk is going to end up, that's kind of analogous to predicting exactly which storm at which particular time the event's going to happen. Where's that tornado going to hit, and exactly how intense is it going to be? No chance. That's like predicting where that Plinko chip is going to end up based on something that happened 10 seconds earlier in terms of where you dropped it on top. No chance. Good luck.
Do you think, though, could there be something that we find one day that would allow us to predict them? Like, if we find this, then we can do it.
I don't think so. There are always going to be these intrinsic limits to to how specific you can make the prediction.
Are you ready for some harder / listener submitted questions?
Always, bring it.
What is the biggest tornado myth?
There's a couple myths that I could talk about, but I would say the biggest one that comes to my mind is that tornadoes form from the top down.
What are some of the other ones?
So some of the others are that tornadoes don't hit big cities. That is not true. So tornadoes absolutely can hit big cities. The difference, or the tricky part there, is that big cities tend to not actually be that big in the context of their footprint. So given the whole amount of vast space that we have in the U.S., cities comprise a very small portion of that footprint. So the statistical likelihood that a tornado is going to hit a city is very small in the first place. But they can, and sometimes do, hit larger cities or skirt the outsides or the suburbs.
There's this idea, I think maybe it comes from too many TV shows involving storm chasers on TV, that the value of tornado observations increases with the decreasing distance that you collect the data from the tornado. Meaning that, hey, let's just have an armored vehicle and drive it right into the tornado. Makes for great television. Don't know that those data are how scientifically valuable they are. I mean, we already know that it's windy in there. We know that the pressure's low. If you actually want to predict tornado formation or understand how tornadoes form or how tornadoes are maintained or how they dissipate, really what you need is observations in a much larger volume surrounding that storm. I mean, a thunderstorm that produces a tornado, it's just keeping the numbers really round. Let's say it's 10 miles in one dimension, 10 miles in the other horizontal dimension, and 10 miles high, 50,000 feet high. That's 1,000 cubic miles, 10 by 10 by 10. That's 1,000. So you need, if you really want to understand what all is going on in there, you need to collect data in that whole volume.
So once the tornado kind of starts, is it fueling the rest of the storm, taking away for the rest of the storm? Like
Yeah.
what's happening with all that kind of energy that's
that's a
there?
good question. A tornado is actually going to be self-destructive to a storm typically because that wind is so strong rotationally at the ground. What happens to the pressure when you have really strong spinning motion? The pressure drops. You can demonstrate this yourself. If you take your coffee, spin it around, the fluid level in the middle drops. And if you spin it too fast, the fluid level drops so much that the fluid level on the sides rises and the coffee will go flying out, right? So the faster you spin it, the lower the pressure gets. Well, if you've got really intense low pressure at the bottom of the storm, that's sucking air down from above. And I already mentioned that typically a tornado is sinking air down the axis, but even the overlying thunderstorm updraft, which can go up to 50,000 feet, you start drawing air downward, and that actually weakens the overlying updraft. So some tornadoes will actually cause the overlying updraft of the storm to weaken dramatically. I've seen even the updraft basically killed by the tornado, and the storm is almost dead, and the only thing alive is the tornado as it ropes out and dissipates, and there's just blue sky above it. Sometimes the storm, though, will then reconstitute itself somewhere a bit farther downstream as the tornado dies, and then you'll restart the cycle again. But tornadoes, in terms of what their direct impact is on the storm, I'd say generally not well studied, but they would tend to have a weakening effect, actually, self-destructive.
What seems to be guiding them? Like once they form, what's dictating where it's going to go?
Tornadoes will tend to move with the motion of the parent storm. They'll tend to drift with that average wind. They tend to maybe move a little bit to the right of the average wind. But that's a good thing, because if they could just move in a completely unpredictable, random way, we'd all be in a lot of trouble, right? So some of the motion of the vortex, because it's so small scale, can briefly deviate a bit from the average motion of the overlying storm. It can't deviate for too long, where it's not going to be with the storm anymore, in which case it'll just peter out.
Most impressive thing you've ever seen or heard of a tornado doing?
I saw a fire hydrant that was literally like sucked up out of the ground with, I don't know, maybe 6 feet or so of pipe, and it was perfectly straight. So it wasn't bent. It was basically like the fire hydrant was sucked right up out of the ground. It was pretty crazy. There's actually a picture that I did not take, but there's a picture of that floating around online somewhere as well. So it's pretty crazy. And then I also was collecting data in a radar truck, and during the El Reno 2013 tornado, and our radar measured the winds that verified that that tornado was the largest on record with a width of 2.6 miles.
I mean, when you're talking about winds that are typically only seen on planets not named Earth, like Venus, for example, you might expect that you're going to have outcomes that are equally surprising.
Climate change, has that affected them in the sense of their strength? There's more of them, they're in different places, or?
Yeah, so putting the climate change piece to tornadoes is challenging because, as we've discussed already, tornadoes are very sensitive to very localized conditions. So you can't attribute ever any individual tornado event to climate change. What we can do is try to assess the impact that climate change has on the larger scale environment and whether or not that is supportive or not supportive moving forward with time. So based upon the data that we have from 1990 to present, there has not been any kind of significant increase in the number of tornadoes on any given year when you look at the full course of that time frame. Neither has there been an increase in intensity of tornadoes. What we do see is a little bit of an increase in low-end tornadoes, so EF0s and EF1s, and that again is primarily a function of our ability to see those areas of rotation using the radar data and saying like, oh, we see rotation there. The National Weather Service warned for that tornado. Did something happen? And there's incentive from the NWS. They want to verify their warnings, right? So they are going to make phone calls. They're going to send somebody out to see if that area of rotation that they warned for actually indeed did produce a tornado. So we do see a little bit of an increase in numbers there, but that again is probably non-physical in the sense that like those numbers were probably always the same moving back into history. We just are better equipped to observe those tornadoes now. What we have seen is a difference in the distribution of locations of where tornadoes are forming and the time of year that tornadoes are occurring. So in a very traditional sense, Tornado Alley, Texas, Oklahoma, Kansas, Nebraska, has always been the mecca for tornadoes in the US and in the world. And it still is. I don't want to slight them from that. But we are seeing a significant decline in the number of tornadoes in that part of the country. And we think that's primarily driven by drought and the fact that in a climate change scenario, we're increasing the robustness of the hydrological cycle. And we tend to be seeing more drought in areas like Texas and Oklahoma and Kansas. And where you have drought, you have dry conditions, you have dry soils. And that's going to be negatively impacting the ability of the atmosphere to actually produce a tornado. So we do see a little bit of a decline in the number of tornadoes in those traditional states, particularly in the climatologically most active months of the year, primarily like late April or early, well, all of May basically, and into early June. Now, to compensate for that, what we are seeing is an increase in the number of tornadoes in southeastern states of the United States. And this is kind of the traditional Dixie Alley that people refer to. So we're looking at Mississippi and Alabama into Georgia and Tennessee. And I don't like to call it a shift because it's not like a continuous thing. It's not like the tornadoes are kind of like starting here and they're edging this way, but instead it's kind of like a reallocation. Like we're kind of reducing the numbers here, but we're adding to the numbers here in a sort of different spatial sense. And those tornadoes are occurring during the cold season. So January, February, March, times of year when we as people tend to not think about tornadoes as being overly important because it's winter time, right? But the link there is retaining heat in the Gulf of Mexico and then the conflict with the cold air that still is generated in polar latitudes. When you have these really strong cold fronts come through, you have really cold air aloft, and then you generate these very strong and dynamically driven low pressure systems. So these are basically your everyday lows, like where you have a cold front and a warm front and drive our everyday weather. In this climate change scenario, those become almost a little bit more robust because we have more heat and more energy stored up in the Gulf of Mexico to contribute to moving on land as that large-scale low-pressure system is intensifying. And then that can cause destabilization and can cause these really deep low pressures that ultimately drive large-scale environmental conditions that are favorable for tornadoes.
Why do some tornadoes seem to jump?
I'm not sure I've really seen that behavior, to be honest. Some will kind of dissipate and then maybe appear to jump if they reform downstream. I would think in some of those cases, terrain is probably playing a role. Some hills or small mountains or valleys or canyons can lead to some locally erratic behavior. In some cases, though, there can be erratic behavior even if you just have flat land without a whole lot of complexity, just because the underlying physics of the parent storm are themselves plenty complicated enough to lead to complicated outcomes.
Since it's just wind, are there invisible tornadoes?
There can be tornadoes that occur without funnel clouds. So again, funnels are not necessarily a function of whether or not there is a tornado. It is a function of the moisture characteristics and the temperature characteristics of the atmosphere as you move up. So you can have, I don't know that you would call them invisible, because if the rotation is strong enough to be a tornado, it's most likely that they're going to be lofting dust and debris from the surface. So you can see the tornado manifest through those visual cues, but you can have tornadoes without funnel clouds.
Best movie about tornadoes, worst movie about tornadoes?
I maybe don't see enough tornado movies, so I've only seen one of, I don't know how many Sharknado movies there are. There's more than five, right? I've seen parts of one. I saw Twister and Twisters. Hollywood film, I mean, to be honest, in Twisters, the most recent one, the technology they were using wasn't really all that advanced. The stuff we use in the field now, you know, we're doing stuff way more advanced than what they were doing in Twisters. And they had this thing, they called it a phased array radar. I mean, we've been using those for 15 years in the field. So, and the ones we have are better than what they had in Twisters. So, that's okay. I mean, this idea about shooting rockets into the storm to affect tornado formation, honestly, the way they wanted to disrupt tornadoes is actually the way you'd probably want to go about doing it. You might not remember the details, or you might remember them, but they were trying to create more cold air in the storm. So rain falls out of a storm, rain evaporates, that produces cold air. And that cold air, for a long time, we believe it's important, one of the important pieces of tornado formation, in fact. But if you produce too much cold air, there's a lot of evidence that can be disruptive to tornado formation. So they were trying to get the storm to coax it into making more rain, I guess, and then therefore more evaporatively cooled air to short circuit tornado formation. So they were absolutely barking up the right tree. But this idea that you can shoot a few rockets into the storm to pull that off is kind of funny, because as we said, if the storm very roughly is 10 by 10 by 10 miles, 1,000 cubic miles, you need a lot of stuff. A few rockets of stuff is, it's like, standing in front of a bus and throwing a wiffle ball against it and expecting that the bus's forward speed to be significantly altered. I mean, it'll have some effect, but not one that's measurable. So anyway, yeah, I enjoy these films. I don't really have one that I would say that I have a particular disdain for.
Oh, what do you personally find to be the most interesting thing about tornadoes? Like the most interesting fact, like that's, to me, I'm fascinated by that.
I've always been fascinated, maybe not so much by a fact, but by this interesting paradox where you look at a tornado, and to me they're beautiful. I think tornadoes are just spectacularly beautiful, and that's one of the reasons that I was drawn to them as a child in the first place, because they're just amazing creations. And then simultaneously, the violence and the destruction that they can cause is just such a paradox that it's sad but amazing at the same time, and of course I would, my heart goes out to anybody who's been impacted personally and has lost loved ones or property or anything that, of course. But just this awkward paradox of beauty coupled with this destruction.